So last time we met definition 2.1 about divisibility. We considered it in a very formal way, but of course, you know, it's something you're all very familiar with, the idea of one integer being divisible by another one. I'm talking about multiples of integers. But we presented a very B divides A if and only if there exists some other integer C such that A is the product B times C. And we have the notation B straight line A. So red, you read that out in English as B divides A. So it's potential for error here is you read this the wrong way and you say it's saying that B is divisible by A, or A is dividing B. That's not what it says. It says B divides A. So the straight line symbol means it divides. And we then went through a number of proofs, and this was all the parts of theorem 2.1, and these were basic properties that the divisibility relation has. Everything divides itself. Divisibility is transitive. Okay, so we discussed all these last time, and they were all proved by using and by constant recalling of the definition. Okay, that's what we did last time. Okay, so we're going to go on today. What today's lecture is going to be about is about the greatest common divisor. Okay, so we'll meet that in a moment. First of all, just to say that, you know, we can actually, since we've defined what divisibility is, we can actually say what the definition of a prime number is now, formally. And a prime number is simply a number whose only divisors, what's that? Positive integer greater than 1, whose only divisors are itself and 1. Okay, so it doesn't have any other divisors. Okay, so I'm hoping everybody knows what a prime number is. So these are the first few prime numbers, 2, 3, 5, 7, 11, 13, and so on. Now we've got chapter 3 is entitled primes and is all about the prime numbers and various properties of them. But just looking ahead a little bit at where we're on the way to, what we're building up towards is this theorem, and it's got this grand name, fundamental theorem of arithmetic. The fundamental theorem of arithmetic says, this is why primes are so important, in one way, that every integer, every positive integer, factorizes as a product of prime numbers, but crucially does so in an essentially unique way. That's the fundamental theorem of arithmetic. We're going to prove that in chapter 3. But we can actually prove half of it. We can actually prove the existence of the unique factorizations already, just using a simple argument based on divisibility. Okay. So, for instance, I should have prepared a bit better. So let's take a number like 210. Okay, we look at it a bit. We ask ourselves, is that a prime number? No. Why? Why isn't it a prime number? Divisible by 2. So straight away you can factorize it as 2 times 105. Are those prime numbers? No. Why? Sorry? 7 and a 3. Are those prime numbers? Yeah, all of those are prime numbers. So we can do this kind of thing is called a factor tree or factorizing tree of a number. All we did was operate the idea of divisibility and writing a number as a product of other numbers. And here we have 210 as factored into primes as 2 by 3 by 5 by 7. So essentially we could construct a formal proof now that such prime factorizations always exist for a number. So if a number is prime, if a number is already prime, then it's already factored as a product of prime. It's just a product of that one prime. If it's not prime, then you can factorize it. So we did. So you called out a factorization of this, 2 times 105. Then we asked, are we looking at primes yet? Well, 2 is a prime, but this isn't. So if it isn't a prime, that means you can factorize it. You keep iterating that process. And because the numbers are getting smaller, and the numbers are always positive, this can only go on for a finite number of steps. Yeah? So you're starting at some point, the numbers are getting strictly smaller as you go down, and they're remaining positive, so eventually you must hit the smallest possible numbers here. But what maybe isn't so obvious is the uniqueness of this prime factorization. So who's to say that there isn't some other way of writing 210 as a product of prime numbers? Okay, because this factorization tree isn't unique. We decided first to factorize this as 2 times 105, but equally well, we could have 3 times 70, 3 times 70. We could have factorized it as 3 times 70 to begin with. Okay, and then we would have factorized 70, and if we kept going, eventually we would have found these exact same numbers. But the question is, how do you know you will always find, that there's just one set of prime numbers that are, for any given starting value, and no matter which way you factorize it, you'll always end up with just those prime numbers, okay? So that's the question, and that's maybe not so easy to see here. And especially if this number we're starting off with is like a gigantic, huge number, who's to say that of all the millions and millions of different choices you can make factorizations at each stage, who's to say that you will able to prove uniqueness of this is there's nothing in what we've said so far that can kind of give us an idea of how to get at the uniqueness for this. Okay? So the question is proving uniqueness. How to prove that? Okay. So, well, what will allow us to prove the uniqueness is a proper is just building up some more theory about the idea of divisibility. Okay. Especially when we look at this idea of common divisors. Okay. This is what we're coming on to now. So we'll introduce the definition of common divisors and greatest common divisor, and then we got a few, a few things to say about it in the chapter, and we'll prove one of them today and do a bit of work with it today. Okay. But first off, the definition. So this common divisor. So we speak about the common divisors of a pair of numbers. So if you've got a pair of integers a and b, a number c is a common divisor of a and b. It's nice and simple. If and only if c divides a and divides b. So it's more or less just what you'd think it would be just from the name. The common divisor c of a and b is something that divides a and divides b. It's common to both of them. Common to both of them as a factor. Okay. So, for instance, let's stick with the 210 actually. So some common divisors of 210 and 78. No. 98. Does that have common divisors? Yeah, there's plenty. 2. 2 is a common divisor. Anything else? I think 7 is as well, yeah. Any other common divisors? Any other number that's both a divisor of 210 and 98? Well, because 2 and 7 are, you can automatically make another one then, can't you? 14. So you can multiply the 2 together. So you get the idea. These numbers, they all divide 210. So 2 divides 210, and 2 divides 98. And also for the other ones. 7 divides 210, 7 divides. So those are common divisors. So given any pair of numbers, any pair of integers, do a pair of integers always have a common divisor? At least one?
Yeah, two.
So if there's two numbers, 2 doesn't have to be a common divisor because one of the numbers could be odd, couldn't it? 3. Sorry? Yeah, well, the number 1 is always going to be a common divisor because remember we proved about divisibility that 1 divides everything. Or did we prove that necessarily? Yeah. So for all integers a, 1 divides a. Okay. So given any pair of integers, at least 1 is a common factor. Maybe there's other ones. Okay. So the set of common divisors is always non-empty for a given pair of integers. So that means we can talk about definition 2.4, which is the greatest common divisor. And it is exactly what it says it is. The greatest common divisor of a pair of numbers is simply the largest number that divides both of them. The largest number that is a common divisor of the two of them. So it's a common divisor, the greatest common divisor of 210 and 98. Fourteen is the largest number that divides, that is a common divisor of 210 and 98. Coprime numbers, coprime pairs, pair of integers is coprime if and only if the greatest common divisor is just 1. So that means the only positive common divisor of the pair is 1. So 210 and 98 are not coprime, but a coprime, you can easily write down some examples of coprime pairs. Just put down 2 integers that don't share any divisors apart from 1. So, 36 and 36 and 49. 2 numbers. Does 1 divides both of them certainly? No other positive integer divides both of them. You can kind of see that if you look at their prime factorization. So the prime factorization of 36 is what, 4 by 9, so that's 2 squared by 3 squared. And 49 is 7 by 7 squared. The fact they're coprime, we can observe that because there's no overlap between the prime factorizations. There's no prime appears in both. Okay. Whereas the prime factorizations of 210 and 98, when you look at those, well, 98 is 2 times 49, so it's 2 times 7 squared. And the 210, its prime factorization is 2 by 3 by 5 by 7. Well, interestingly, the GCD of these two, 210 and 98, you can see from this example, can you characterize the GCD? We've already said it's 14. Can you characterize it in terms of the prime factorization? How would you describe what the greatest common divisor of these two looks like with respect to their prime factorizations? It's the overlap, yeah. 2 times 7 squared, and this has a 2 in it, and it's got 1 7 in it. So it's the overlap. That's true in general. That's something we'll be proving. Once we've established the fundamental theorem of arithmetic that we referred to a while ago, that any integer does factor uniquely into primes. So if there's a unique list of primes, you can talk about that the factors of any integer, then we'll be able to establish this fact that the greatest common divisor of any two numbers is just equal to the overlap, or the intersection, if you like, in the two prime factorizations. And that gives a nice way to explain or to say when two numbers are coprime, they're coprime when their prime factorizations do not have any overlap, when they're completely distinct, feature distinct primes. Okay. So any questions or any queries about anything we've said so far? Okay. So that's just a load of definitions and a few illustrations of some of these terms. But we're going to get into some close arguments now. So what is it about the greatest common divisor? Well, there's two main facts that in the next lecture. In the next lecture, we'll be looking at something called the Euclidean algorithm. The Euclidean algorithm is an algorithm which, given any two numbers, spits out their greatest common divisor. Okay. And you don't need, it doesn't work by using their prime factorizations, which is how I've kind of explained the form of the greatest common divisor here as the overlap in the prime factorizations. It does it in a different way, just by kind of trial divisions and so on. And so we'll be looking at that next time. So there's the existence of a good, efficient algorithm for calculating greatest common divisors. But the other results we're going to look at today, this is theorem 2.3. I know I'm hopping around a bit, but just pointing the various things out. This characterization of greatest common divisors in terms of linear combinations. So this is going to be the central result that we're going to work to today. And this says that if you're given any two integers a and b, okay, we can refer to their greatest common divisor, d. And this says that the greatest common divisor can always be written as a linear combination of the two numbers. That's interesting. So what this is saying, for instance here, this is saying that 14, it must be possible to write 14 as something times 210 plus something times 98. So we must be able to find an n, an integer n and another integer n, such that you can express the greatest common divisor as n times 210 plus n times 98. And the coefficients n and m, they can be any integers. They could be positive or negative. But once you know that the greatest common divisor can be written like this, you then automatically know that any other common divisor of a and b. So if you've got another common divisor of a and b, something divides a and something divides b, that means it must divide d as well, because you've been able to write d as a linear combination of a and b. Okay. And one of the properties of theorem 2.1, going back to the last lecture, was, and I said it was going to crop up loads and loads, this divisibility of linear combinations. If you got a divides b and a divides c, well, we understand that now as saying that a is a common divisor of b and c. If a is a common divisor of b and c, then it divides every linear combination of the two numbers. So coming back to this theorem, which we're going to prove now, once we know that the greatest common divisor of two numbers can always be written as a linear combination of them, that means that any other common divisor of a and b, not necessarily the greatest one, it must also divide that number d as well. Divide that greatest common divisor. So this leads us to this this other characterization of the greatest common divisor, which you can sum up nicely in one phrase, and I think it's the first kind of non-obvious fact we're going to prove in the course. You know, all the little results we've proved so far, I don't think any of them came as a shock to anybody. I don't think anybody was shocked to find out that divisibility was transitive, for instance. If something divided b, if something divided b and b divided something else, then the first thing divided the last. That meshed well with our intuitions. I don't think it would have struck anybody as surprising. But this theorem 2.3, I think, is the first genuinely kind of non-obvious result like this, because it's going to enable us to say, I don't quite have this spelled out as such, I think it's spelled out after the proof. The GCD of A and B is the small. This is another. This is a consequence of this theorem 2.3. It's the smallest positive linear combination of A and B. Okay, so linear combinations of A and B are objects that look like this: m times A plus n times B. Linear combination, I guess we should say, although it's kind of implied, with integer coefficients. We're only talking about the n and m being integers. It's the smallest positive number which has this form. And that's the greatest common divisor of the two. Okay. And it kind of functions as it brings addition into the picture, okay, because we define the greatest common divisor only talking about divisibility. That only talks about the operation of multiplication. But after we prove this theorem 2.3, we see nicely the operation of addition coming in again. Okay, and that kind of ties the whole thing together. Okay. Any questions just about the statement of it? Statement of theorem 2.3. Given any two integers, the greatest common divisor can always be written as a linear combination. And moreover, that linear combination, it's the smallest positive number that you can produce as a linear combination of A and B. That is the greatest common divisor. Now, in order to prove this, we're going to have to use this tool, theorem 2.2. And again, like the definition of divisibility, this is, although it mightn't look familiar straight away, it's presented in a very precise, formal way, but it is just establishing something quite familiar to you, I think. And this is the process of integer division with remainder. Okay. What this says is, if you're given any pair of integers A and B, as long as the B is non-zero, then there exists a unique pair Q and R such that you can write A Q times B plus R. And R, and it's called R because it's a remainder. Q, the term Q is used because this is referred to as a quotient of A by B. The remainder term is a positive term, and it's got absolute value less than the absolute value of B. So this is the process of integer division with remainder. Let's just look at some examples. Okay, so this is in Sage, just doing a few examples. So for instance, we can write 101. We're going to divide it by 37. So we have A is 101, and we're going to try and divide 101 by 37. Of course, it doesn't divide in evenly. We don't say that 101 is divisible by 37. But we can fit 2 copies of 37 in there. We can take 2 multiples of 37, and then there's a small remainder term, 27. Key thing is that remainder term is less than the number that you're dividing by. Yeah. Make the numbers a little bit bigger. Okay, 10,134. We can try and divide that by 371. We find a certain number of multiples of 371 there, 27. If we went to 28, we'd have gone too far. Yeah? If we went to 28 times 371, we'd have popped above that number. But we can go this far, 27 multiples of it, and then there's a remainder term of 117. The point about the remainder term is it's positive and it's less than the number that you're dividing by. Now, how did I calculate the Q and R here? Well, you see I divided A by B. Now, in general, that's not going to be an integer. It's going to be a rational number. But I took the floor of it. The floor is this function that gives you the largest integer less than a given real number. The floor of something it's the integer floor of a general number, general real number. It's the largest integer smaller than that number. when you take the floor of the actual fraction, a divided by b, that gives you the quotient q, and then the remainder term is simply the remainder. So when you take q times b away from a, you'll be left with this small remainder term, which the computer is printing up there. So this is kind of the clue to it, to proving the result that yes, q and r will always exist because we can come up with this way of calculating them. But there's also this uniqueness part attached on as well. So not only can we divide a by b like this, so we process of division with remainder, but we can do so uniquely. The pair q and r are unique. Okay. So for any given pair of numbers a and b, there's only one q and only one r, which do this division process, and with the r being a small remainder, okay, with value of r less than the absolute value of b. Now the way this is proved is with really it's a proof by induction, but we use an alternative phrasing of the induction principle. Okay, and this is what's known as the well-ordered principle. So this was back in chapter 1. Now I didn't refer to it too closely back at the time. So the induction axiom was axiom 11 back here. But I had an 11a and 11b. 11a was the induction axiom, and 11b was the well-ordered axiom. Okay, but I'll put a slightly different phrasing of this up now on the board. It's, as I say, it's an alternative way of expressing the principle of induction, but it looks quite different, or it seems quite different on first inspection. But you can prove that it's equivalent to it. And we won't go through that proof today because it's a little bit technical and it kind of takes us away from the main focus on common divisors, but we may go through it in the future. So this is the well-ordered principle, well-ordered axiom principle for the integer z. And what it says is, it says every non-empty subset of the positive integers has a least member. Smallest element, least element, or smallest element. Every non-empty subset of the positive integers has the smallest element. Now, this appears to be quite obvious. I mean, if I give you a subset of positive integers, if I throw in a load of positive integers here, all it's saying is that one of them will be the smallest one. That's all it's saying. Not that controversial for a set of a small number of integers. Okay, if I write in, I mean, it's not even writing it. It's not even worth writing in an example. If I just put a bunch of integers there, a bunch of positive integers, one of them will be the smallest one. And even if the set is infinite, even if it's an infinite set of positive integers, it still has to be one of them there that's the smallest of all the others. Okay? So you can just start counting up 1, 2, 3, 4, and just asking, at some point you're going to meet a number that is the first time you meet an element of the set. Yeah. So that has to be the least element of the set, if you think about it. Yeah. Is 1 an element? Well, if it is, then it has to be the least element of this subset of positive numbers. If it's not, check 2. If it's not, check 3. If it's not, check 4. Eventually, you'll find the first element of the set. Well, that's the smallest one. Okay. Of course, that already should remind you of the induction principle. So you're doing something here like starting at 1, then moving on to 2, checking 3, and so on, with the understanding that this takes you through all the integers. Right? Now this property is not true of the rational numbers, say. So again, it's something equivalent to induction. It characterizes the integers as being distinct from the rationals or the real numbers, okay? Because remember, the rationals and the reals, they share loads of algebraic properties with the integers. The operations of addition and multiplication, the rationals and reals, you know, they have the same algebraic properties as the operations on the integers. But it's this kind of fact which separates the integers off. So can someone give me an example of a subset of Q plus, subset of the positive rationals that doesn't have a least number, that doesn't have a least element? So it's the set of all positive rationals, so all rationals bigger than 0, with some property. Can you give me that property, an example of one, that would be a set which has no least element? So it must be something which you can't do with the, you know, something that wouldn't work with the integers. Because every subset of positive integers will have a least element by this principle. Anybody got an example for the rationals? Sorry?
Decimal.
Well, yeah, every rational can be written as a decimal.
Yeah.
It's not as complicated as that. So some bunch of rationals, which is well defined, positive rationals, but which doesn't have a least element. Sorry? 1/3. Well, that's just a single rational number. I want you to give me the condition that describes a subset of rationals. Or what were you thinking with the third? Or say,
1 over n.
1 over n. Okay, so you're saying every rational number which has the form 1 over n, and what's n? What are you allowing as n?
Or any. No, sorry. Yeah, any prime.
Any prime number? Okay, cool. Okay, so this is the number 1 over 2. The number is 1 over 2, a third, a fifth, a seventh, and so on. Greater than. Well, I mean, why do you want to leave out 2?
Because 1 over 2 is exactly 0.5, 0.5. So 1 over 3.
Yeah, but I don't think. But as long as you know, as long as you accept that there's an infinite number of prime numbers, of course, which we haven't proved yet. Because you see, if there's only a finite number of primes, then this will just be a finite set like this, and so we will have a smallest element. Any finite set of numbers will have a smallest one. It's where things happen with infinite numbers. Okay, there is an infinite number of primes, and if you understand that, then there won't be a smallest number here. But you don't have to introduce the idea of primes. You could just make it simpler. Just consider every Q which has the form 1 over n, where n is a positive integer. So then you'd be thinking of a half, a third, a quarter, a fifth, a sixth, and so on. And it's in, it keeps going. The success, the smaller and smaller numbers there. There's no smallest element. There's no smallest element of this set. Everybody accept that. Because if you claim there is one, well, it has to be of the form 1 over n for some positive integer n, but then the next one, 1 over n plus 1, will be a smaller one. So there can't be a smallest one.
But 1 over 1 would be rational.
1 over 1 is rational, yeah. Okay. See, the rational numbers contains the integers. The rationals are everything that can be written as a as a fraction n over m, where n and m are integers. So that includes 1 over 1. That includes the integers themselves. The point is, this set has no smallest element. Or another example would be the set of positive rational numbers that were strictly bigger than 1. Just look at all the rational numbers that are strictly bigger than 1. So all the rational numbers you can find on the number line that live over here. All the rational numbers you can find over here. Now, is there a smallest one of these? No. I mean, if I'd included one, then there would be. 1 is the smallest number, but I haven't included 1. I'm just looking at everything strictly bigger than 1. It's an infinite set of rational numbers, and there is no smallest element in the set. So whichever one you try and make the smallest, say something really close to 1, there'll always be an infinite number up and still that you can squash in between that number and 1. Okay. So this well-ordered principle is not enjoyed by the rationals or the real, and similar examples work for the real numbers. Okay. But it is a property that the integers have, and it's equivalent to induction, equivalent to the principle of induction. Okay, and you can kind of see that here as well. So the principle of integer division with remainder, that can be formally proved using the well-ordered principle. Now I won't go through the proof of that here. It's pretty straightforward because I want to focus on the proof of 2.3. This is the really interesting result. Okay. So this is this thing I was talking about, that the greatest common divisor of a pair of numbers can always be written as a linear combination of the two numbers. And we're going to talk through the proof of it here, and I think finish by looking at an application of it. So let's look at the proof. What we're trying to do is show that given A and B, the greatest common divisor can be written as a linear combination. So the way the proof works is, and it's going to operate with this well-ordered principle. So what we want to do is set up a certain set of positive integers. The set we're going to use is the set of all the positive linear combinations of A and B. We're trying to prove that there's certain kinds of special linear combinations of A and B, or one particular special one, which happens to be the greatest common divisor. So we consider the set of all of them, all the positive linear combinations of A and B. So S is this set of every number which is alpha A plus beta B. The alpha and beta are integer coefficients, and the linear combination must be positive. Okay. So this S is a subset of the positive integers. So it's something that this well-ordered principle can apply to. So by the well-ordered axiom, or principle, this set S has a least element. We're going to call it D. And then what we're going to prove is that D is the greatest common divisor of A and B. So this number D, remember, it's a positive number, so it comes from the set S, and the set S only contains positive numbers. And it's also a certain linear combination of A and B, because that's what the set S is. It's the set of all, everything in S is a linear combination of A and B. So we've got positive linear combination of A and B. And it's special because it's the smallest one in S. That's what's special about it. Now we're going to prove that it is also it also is the greatest common divisor of the two numbers. So we claim that D is a common divisor of A and B. Yeah. So first of all, we're just proving that it is a common divisor, not that it's the greatest common divisor. Just that it's a common divisor. Now, how do we prove that? Well, the case we have to, the possibility we have to consider is that it didn't divide A, or it didn't divide B. That's the only way it could fail to be a common divisor. If it fails to divide one of them. So suppose that it did not divide A. Well, if the number D did not divide A, then you could run through this integer division with remainder process. And you could write A There's a certain number of d's plus a remainder, but crucially now the remainder is strictly between 0 and d. Okay? So we're supposing that d does not divide a. So you get a non-zero remainder. D does not divide into a evenly. There's a bit left over, and this bit is r. But then you focus in and you examine r again. Well, r can be written as a minus qd, just reversing this equation. But d we have already is a linear combination of a and b. You can replace d by that linear combination. And then you gather all the a's together, and what you discover is that r is a linear combination of a and b. R is a linear combination of a and b. It also is a positive number. So that means r is in the set S we set up there. Then there's something else funny going on. R seems to be strictly less than d. But it can't be strictly less than d because d came to us as the least element in S. So this is like a little proof by contradiction. We suppose that d does not divide a, but then we find that d is no longer the smallest element in S, which is a contradiction because it is. That's where we got it from. So that's a contradiction. So what we do is the conclusion is, well, the assumption that led to that contradiction has to be false. So we can't have contradictions. If there's contradictions, then everything, literally everything falls apart. Reality falls apart. There are mathematical contradictions. So the thing that led to the contradiction was this assumption here, that it was even possible that d did not divide a. So that can't happen. So it must be that d divides a. Then you can run exactly the same argument focusing on b. If d does not divide b, again you get a contradiction. So d must divide a and it must divide b, so that means it's a common divisor. And then to get that it's the greatest common divisor, then we're using the linear combinations result about divisibility from theorem 2.1. If e is any other common divisor of a and b, then e has to divide d, and therefore it is smaller than it. Okay, so these are positive numbers. So d is the greatest common divisor, and all other common divisors divide that number d. Okay, I didn't get to the application, but next time, so in our third unit lecture this week, you see there's a bunch of questions that you meet straight away. So you should start looking at these, and I'll work through some of these in the next lecture, and we'll look at the Euclidean algorithm as well. So the next lecture will be a lot more accurate.